Let's come back to the ball on the ball on a string, but this time let's have it going on a vertical circle, so that there's gravitational force is pointing down in the plane of the circle now. So there is a gravitational force at any point, Fg, on that ball, wherever it is in the circle. And it's on a string, it's a taut string, so there is a Ft in the string. And I want you to just notice that as you go around the circle, Ft and Fg change angles between each other. Okay, anyway, that's just for later. If the ball is rotated at approximately constant speed, it's actually impossible to rotate a ball in a perfect circle at constant speed in a vertical circle. But anyway, approximately constant speed, what is the maximum speed at which the string will not break if the string can only withstand a force of a tension of up to 150 newtons? That says Ft max, right? A maximum tension of 150 newtons above which the string will break. Let's give you some parameters. The mass of the ball is 200 grams, which let's just change those units right now to 0.2 kilograms. And the length of the string is 60 centimeters. Change those units right now to 0.6 meters. Okay, just to keep everything in MKS units. Now, let's figure out how to figure out what is the maximum tension. We got to draw a free body diagram of the ball. But let me just jump ahead and just say, hey, wait. We got to draw a free body diagram of the ball where? I just said that Ft and Fg are at different angles, right? So think about it. Think about, for example, whoops, what was that? Sorry, hold on. So let's just think about the ball in a couple of positions. The easy positions to think about are at the far right, at the top, at the far left, bottom, and far left. Those four positions. Let's just think about the ball at those four positions. Let's draw a free body diagram of the ball at each of those four positions. And just to keep you in the game here, let's draw the free body diagram on the diagram, which is not what you're supposed to do. But I'm going to draw the free body diagram for each of those positions on the diagram, just so that we can make sure we understand what we're talking about. Okay, so for example, let's take the ball at the top. What are the forces on the ball at the top? The forces are, of course, there's always gravity pointing down, Fg pointing down. And then what else is touching the ball? Make sure we understand the blue circle is just the circle that it's going in. The blue circle is not a physical thing. That should be really a dotted line to indicate the path of the ball. But anyway, okay, Fg, and it's attached to a string. Right? So at the top of the circle, what's the direction of the tension of the string? The tension of the string is always pulling it towards the center of the circle. It's a taut string, so Ft pulls it towards the center of the circle. So there's two downward forces. Let's take the ball on the left. On the left, what are the forces on it? It's the same two forces, gravitational force down and the tension in the string. But what's the direction of the tension in the string? It's always towards the center of the circle. So now we should be able to answer this for every other position. At the bottom, gravitational force down, and the tension of the string is towards the center of the circle. On the right, gravitational force down, and the tension of the string is towards the center of the circle. So those are four separate free body diagrams. So I would claim that if we sort of understand what's going on in those four positions, we could actually imagine what's going on in any position in between. So let's just go ahead and think about those four positions. Actually, okay. So let's just take, for example, let's take the top. Let's take the top. Let's start with this one. Okay, let's start with that one. Let's apply Newton's second law. First of all, we got to choose our positive directions. Try to choose our axes. What direction is the acceleration? The acceleration is towards the center of the circle. Always, centripetal acceleration when you're going in a circle is towards the center of the circle, unless there's also a tangential acceleration, but there is always a centripetal acceleration towards the center, and this is uniform circular motion, where the centripetal acceleration is v squared over r, and it's pointing towards the center of the circle. Okay, we know that. So I'm going to choose downward as my positive x-axis for the ball at the top. And so I can then apply Newton's second law. So for the ball at the top, Newton's second law, F net x equals max. Look at the net force from the free body diagram. We've got plus Ft plus Fg. Those are the two forces. They're both pointing in the plus x direction, equals the mass of the ball times the acceleration, which we know is v squared over r. So that's Newton's second law for the top. Okay. So what is the tension? Therefore, the tension is equal to mv squared over r minus fg, which is mg, right? So therefore, the tension is mv squared over r minus mg. So that's the tension at the top. So now let's look at a different one. Which one do you want to look at? The right one? Okay, so let's look at the one on the right. So on the right-hand side, the one on the right, that's this one, yeah? Okay. Let's choose the direction of acceleration first, because that's always the direction plus x, or that's what we try to make direction plus x. The acceleration, the acceleration is, as always, towards the center of the circle, uniform circular motion. And so I'm going to choose to the left as plus x. And this is now two dimensions, so let's just go ahead and choose down as plus y, since the other force is in the down direction, plus y. Sorry, it's a little messy. Okay, so let's apply to the ball on the right, the ball at the right-hand side of its circle. F net x equals max, F net x equals max, F net y equals may. Okay, let's take F net x equals max and look at all the forces in the x direction. In the x direction, we got Ft equals, that's filling in the forces from that's the next step, filling in the forces from the free body diagram, and then equals m. Let's go ahead and fill in the acceleration, v squared over r. There, we're done, right? That's the tension on the right-hand side. We don't even need the y equation. We don't need the y equation. What the y equation tells us is that Fg equals m. It tells us that there is actually a tangential acceleration. This is an aside. That's why it's actually impossible to make it go at constant velocity in a perfect circle. But we're ignoring that right now. We don't need to know that in order to answer the question, what is the tension? The tension is mv squared over r. Okay, so now actually let's just go look at the left-hand side. Say, obviously, I hope it's obvious, it's the exact same thing. We've got the acceleration towards the center, so we're going to choose plus x to be to the right, and we're going to end up getting Ft equals mv squared over r. Okay, so that's on the right. So at the top, the tension was mv squared over r minus mg. At the right and left, what happened? On the right and left, the tension is at just mv squared over r. And what about the bottom? Let's go ahead and do the bottom. The acceleration is towards the center of the circle, so I'm going to choose towards the center of the circle as the plus x direction, or up as the plus x direction. And now both Ft and Fg have x components, and Ft is in the plus x direction, and Fg is in the minus x direction. So minus Fg equals ma, mv squared over r. Acceleration is v squared over r. And so therefore, Ft is equal to mv squared over r plus Fg. Okay, so to summarize, just writing everything on the same page, we now have the tension at those four positions. So now just look at that and tell me, where's the tension the largest? Remember, we're in uniform circular motion, which means v is a constant, or is approximately constant, because we explained that. R is a constant, that's just the radius of the circle. M is a constant, that's the mass of the ball. So where is the tension the largest? The tension is the largest at the bottom, where the gravitational force is pulling on the ball away from the string, so it's pulling to increase the tension, right? The tension is the largest on the bottom, and where is the tension the smallest? Tension is the smallest at the top, where the gravitational force is pulling down to help alleviate the tension on the string. The gravitational force is helping the ball move in the circle, actually. And so the tension is the smallest. And so, and the tension on the right and left are somewhere in the middle. So what happens to the tension as we go around, right? Let's just start at the bottom. It's largest at the bottom. It gets smaller as we go around. Smallest. Tension is smallest at the top. And this has to get largest at the bottom. Okay, so the tension changes continuously as you go around the circle. So where is it most likely to break? It is most likely to break where the tension is the largest, at the bottom. So we can calculate the tension anywhere, but now that we understand the concept of what's going on, we could, if we understood to start with, we could have gone right to that position saying we understand that the tension's got to be the biggest at the bottom, so just calculate it at the bottom, because the question was where's it likely to break, or what speed is going to make it break, or what's the maximum speed. And so the answer is that maximum at the bottom. So that's where we have to calculate its maximum speed, and the tension max is 150 newtons, and so we can go ahead and calculate the speed. Therefore, actually I'm going to wait to plug in the 150 newtons till the end, so let's just keep Ft max. So I just solve for V, and V max is 21.1 meters per second, and I checked the units, and they all make sense, right? Meters per kilogram cancels correctly to give us meters squared per second squared under the square root, and we're left with 21.1 meters per second. That's kind of fast, right? 40 miles an hour, although it's not completely unreasonable. It's not unreasonable at all. I mean, the fact is that if you got a ball on a string, 150 newtons seems quite reasonable for a string maximum tension. You got to rotate that ball pretty darn fast before it breaks. That's going to hurt if you hit somebody with that ball while you're rotating it. Okay, there you go. Have a wonderful night.